So what we're looking at here in number 7 is an E cell problem, so we're using the Nernst equation. We're told here that the reduction potential for X5 plus is 1.48 volts. So your starting point in this problem is realizing that the actual reaction that we have is this one. Now it's X5 plus, which means we need 5 electrons here to neutralize that and have it become X solid here. Now you know it needs to become X solid because that's what we're told over here, so we're getting X solid as a product. Now this is 1.48 volts. Now the other thing we're told is that this over here is at the beginning, which makes it the anode, which means oxidation is going to be occurring at the anode, which means the first thing we're going to have to do is switch this around and turn it into an oxidation. So we'll do that. We'll make it X gives X5 plus 5 electrons. And the voltage now is going to be negative 1.48 volts because we had to switch it around. Now the other one is MnO4 minus MnO2 and H+. If we look at the reduction potential table, we'll come up with this reaction that will match all of those ingredients. And I've taken this directly off the reduction potential table. That has a voltage of 1.70 volts. Now to come up with the actual balanced equation here, I'm going to have to multiply this by 3 and multiply this one by 5. And when I put it all together, this is what I'm going to end up with. I'm going to end up with a 3x solid plus 5 MnO4 minus plus 20 H plus, giving 5 MnO2 plus 10 H2O plus 3 X5 plus. And then when we add the voltages together, we're going to come up with positive 0.22 volts as this is going to be our E0 cell, because this will be under standard conditions. We're going to need to use the Nernst equation, and the Nernst equation is E cell is equal to E0 cell minus 0.0592 over N times log of Q. Now the N value is going to be the number of electrons transferred in the balanced equation, and that's going to be, in this case, 15. That's 3 times 5, because when you multiply 5 by 3 you'll get 15. 3 times 5, that's 15. So our N value is going to be 15 as well. We still need to get a Q value, and we'll do that by doing products over reactants. And we got X5 plus cubed over MnO4 minus to the 5th and H plus to the power of 20. We substitute in those values, and we're going to get to now the values I'm talking about are the ones that were given in the actual problem here, and these are the actual concentrations of these species in solution. You'll notice that when we do the Q value, we don't include solids and we don't include water, and that's a solid as well. So all we're interested in are the things that have concentrations in solution, and not coincidentally, those are the ones that actually have concentrations listed in the problem. Now the X5 plus, that's 0.48. Not going to worry about units here. Q doesn't need a unit, so I won't worry about the molar here. So I'm just substituting in these values as they appear in the problem. And we'll end up here with 210,553. I'm not interested in significant figures here so much. I'm just trying to get the best value I can here. Now log of Q, that's log to base 10, is going to be 5.32. I get that just by doing the log button on this number in my calculator. Now the E0 cell, that's 0.22 volts, minus 0.0592 over 15. I told you that was the N value, N equals 15. The number of electrons transferred in the balance equation, multiplied by 5.32 over here. This will come out to be 0.22 minus 0.0210. When we adjust this for significant figures, that's 2 decimal places, that's 4 decimal places, the answer comes out to 2 decimal places. It'll be 0.20 volts.